Hi, my name is Stephen Armour. I'm with myLCars, and in this tutorial I'm going to be showing you how to create a Verilog modules and Verilog test benches from Python's myHDL. myHDL is a Python library that allows you to write pseudo HDL code in Python that can then be translated to either Verilog or VHDL, with making you language agnostic. And in my opinion has several benefits over traditional HDL. One of which is its use, which I'm going to go over. To start off with, one of its major benefits is that not only are you writing in Python, which is much cleaner of a language than Verilog or definitely VHDL, but also you can use the Jupyter Notebook to encapsulate all your documentation, Asian development, and then use GitHub to keep track of it. So to start off, we have our imports. The only two ones that for this notebook are absolute necessary: the myHDL and myHDL Peak. myHDL Peak is a library from Zeiss Corp, which does some really awesome stuff for testing your HDL in the Jupyter Notebook. And then I've written these two additional functions down here that will read back in the Verilog or VHDL code and print it into the notebook. So we're going to jump over to the last one, the last memory module in this notebook, because it's kind of a more complicated one. So it's this read and write memory. So starting in myHDL.10, we have to use an @block awk decorator for any code that we then want to translate it over to the normal HDLs. In here we have our ports or parameters. Parameters at present are not synthesizable over to Verilog or VHDL. They have to be set. They are parameters only within the Python context and must have set values used before they get converted. We have our sensitivity. We have create all our memory. These signals is pretty much an encapsulation for a lot of things, because again, myHDL is language agnostic, so signal covers a wide things. It's your wires, your registers, ERVs, etc. Our int vector creates a integer bit vector. There's a couple ways you can generate this. Look at the documentation, but this is basically creating a 4-bit it. We're using Python on notation, Python numbering, unlike Verilog. So in Verilog, this would be 3 down to 0. In Python, this would just be 4 or colon. And we're creating so we're creating 4 instances of 4-bit memory by using list comprehension. We have our sensitivity list is to our write action, and so this is going to look at that list and set based on the address. This is going to choose our list, our location list. The .next is then going to take the data in and set to that. We have our read action, which is the combo action. There's no sensitivity on it. I shouldn't say no sensitivity. The sensitivity is the combo action, and then we return instances, which will return everything in here. And then we have our test bench. Now this is where we're going to show off what Python can do for testing. And so in here I create the signals above the test bench, and I found them into Peaker. Now Peaker is the main class in myHDL Peak. So we have the signal that we've created, and then we've bound the signal into Peaker. So Peaker looks at this, and again, this is not part of the test bench. This is a really nice add-on. And then we have the name of the signal. We can make this is what it was, or we can make it something that's more easily to understand. Content here is just some dummy information. Then we create a device under test, which is an instance of our RAM current, and we take the signals and we bind them up to their respective locations. If we had other signals, we could do an equal sign, but because the signal names and the signals are one-to-one, just translates over. And then we define a function that incorporates our test bench, which is again like just writing a Verilog test module way. But this one, because our signals are outside, I've used the peaker, is not suited for, and for a couple other reasons, is not suited to be translated over to Verilog. So we're going to have to create a modified copy of this. We have our clock generator because there's not really a clock per se in Python. We define our actual test as within this instance, and so this is going to set values and use as stimulants, and then we do our return instance, and then we take our device and testing as our test bench, and we bind them up in the simulation. We also give it information about peaker, and we hit run, and we get our simulation results. And so what peaker will allow us to do is produce waveforms. There's a lot more information on myHDL peak documentation about things you can do about setting when the start and stop off of the waveform, reordering the waves in the waveform, so on. And Dave, I'm not going to try to butcher your last name. Added the two data frames, so we can take our data out and actually produce a pandas data frame. This is an exceptionally nice feature because we can write a Python module, function or class that generates test data that we know is absolutely valid. It says our reference, and then we can create our test bench, our HDL test bench, into myHDL. We can produce our data frame, and then we can start comparing the data frames and using Python's data processing, and we can do all sorts of stuff that traditionally you'd have to take your HDL, run it through a test bench running program, and like Vivado, you then have to take that data, you'd have to bring it back over into something like MATLAB, or Python, process it and compare, and then make the edits. But in this, we can do kind of everything all one shot. So for instance, I can look at this data frame here, and I can look at what were the signals and the responses, the stimulus and the response for when write enable was true. I can also ask that same data frame, what were the stimulus and the signals and the responses when write enable was false. And then, and again, this is something new in .10, and is we take the instance. We don't go for the actual function like in previous versions. We go after the instance, and we use a .convert on the instance, and so everything's ready to go. And that will actually generate a RAM concur or .v. And so using that auxiliary function I wrote, we can read that back in the Jupyter notebook, and if we know how to read Verilog of VHDL, which the default on this is to Verilog, we can go through and look at and see, right. And honestly, a lot of times, when I've been learning Verilog, I've done things like not put buffers on outputs, and when I do the conversion, myHDL will yell at me and tell me something's not right, which has aided me in my learning process. Now I have run these over in Vivado already, and took screen grabs as the resulting RTL and the synthesis schematics. But here I want to talk about the test bench and that's with the Verilog. So in this, what we've done is we've added the app block to indicate that it's synthesizable, and we're not using peaker at all in here, but we've created the signals inside the test bench. We've created the content, which is just again a tuple, and you're going to have to be kind of careful at this point what you have in here, because this is going to try to run and create the values when it does the conversion. So only things that are, you need to sanitize it basically. You need to make sure it'll work. Next thing we've done is, instead of having a delay on the clock and using the clock being generated via an always, we've done an instance and we've moved the delay, which is 1 nanosecond. So every clock cycle is going to be 1 nanosecond. We can change that after setting a number, or we've done that within the while loop. And then the stimulus in this case is identical to the Python version, and I've done nothing here. The raise stop simulation here, which is identical again to the Python version. When this gets converted, it's going to be the finish signal. And then to actually have Vivado generate the waveforms and actually see the waveforms, we have to write a print statement, and in this case is an always block, which is looking at the positive edge, and we write out the signals we want to look at. We do it to an instance. Then we create an instance of our test bench here. We do the dot convert method on our test bench instance, and explicitly here I've said Verilog initial values is to be true, and then I use the my little helper function, and we can actually see now how the entire our signals have been reset to initial values and we can see that we now have a test bench. And so before I move on to doing some stuff in Vivado, I want to give a huge shout out to Mahar Patel, if I butchered your name, I'm sorry, who wrote the first example I've seen of testbench conversion in his work on FPGA designs with myHDL, which you can find on here. Again, huge shout out, thank you. So now I'm going to switch to Vivado and show you how we now play with the resulting Verilog code. So I'm still working on learning OBS Studio, so just hang on a second. So now we're in OBS Studio, Vivado, and so I've already loaded up all the modules and all the test benches here. So I'm just going to show you how you would have done it. And the thing is, though, the files are located on my computer, and Vivado is going to try to reference this via the file path it's been told. So you're going to have to reload this on your computer. There should be a way to make it agnostic between computers. I don't know it. So on the project manager, and again I'm using 2016.1 on version, I'm going to add sources, and to add the design sources I'm going to make sure I click add and create design source. Let me go add files, and because this is already loaded, it's not going to reload. It's going to give me an error in the technical commands, but I'm just going to say a load. Okay, finish. I got a tickle. It's going to yell at me a big whoop. Now, because I have multiples in here, I need to make sure I have set as top by right-clicking on the module, and then click set as top, which I've already done. And then on the same thing, if I want to run this test bench out of all the, and I don't know why it also copies the module down here, but on the test bench V, I've right-clicked here. I have to set this as top, but to add those, and this is where it gets a little tricky. I need to go add source and create sources. Next, add files. Now you'll notice that there are the TBVs right here, which are the properly convert or test benches to Verilog, and there's also these TBE underscores. These are generated from during the Python test benches. If you look at them real quickly, they're not really, they're not true test benches, Verilog test benches. These, however, are true Verilog benches. So we would click on that, we'd hit OK, we'd add everything, but again, I've already added everything. Now, I can then, and using that top module, I can run the elaborated settings, I can look at the schematic, right? And of course, and it's going to give me a schematic. I can run synthesis and look at the schematic here. Here, I can also do place and route out stuff. I am not that high of a FPGA user, or definitely not a Vivado user, to even start with that. And then from there we can run implementation. Now the reason why I go through that is because if we go back to the simulation and run simulation, we can run the behavioral simulation, which will just work straight on the Verilog, or we can run the post-synthesis and post-implementation Asian functional and timing simulations, which you should definitely run on and definitely do confirmations. And this is something myHDL will not do. This myHDL will do. This is specific to the FPGAs. It is because of what goes on in the FPGAs. And if you're using myHDL for ASIC work, or you would use whatever your synthesizing tool to circuits, you would use its implementation and timing stuff. But let's just run implementation things. And again, this is simple. There shouldn't be any errors. It's running simulation. It's going to give you back the test bench, and it's noting that it hit the finish. And I find this kind of annoying. I go to waveforms. Doesn't look like we had. So you need to click on the waveform, go to full view. And here we can see it isn't going to the internals of the module, but we have all the signals that we were looking at in Peaker. And I'm going to actually bring that up. So I'm going to go back over to that waveform that we got out. And if we look at it carefully enough, we can actually see that our D out was 0 as it started, and then it hit 3, 2, 1, 0, 3, 2, 1, 0, 3, 2, 1, 0, so on. Our address was working the same. We can verify it, and so we can see that we can, and when done properly, I want to add that caveat because I've definitely screwed it up myself. The testing in Python is at the behavioral level is just as accurate. When done right, and writing test benches is art in itself, let alone HDL. Is just as powerful. And because of we can use all the Python, might be even more powerful at the behavioral level than what we would get in a synthesis tool like Vivado. Now I also want to show something. I'm going to go up to the very first memory here, which is a simple ROM that's preloaded with values. So it's a read-only memory, and I want to demonstrate something, and it's actually really cool and powerful. So Vivado knows where this resulting Verilog file is, and it reads it in. The thing is, though, and I don't have the greatest understanding of how to set all the controls in doing this, is that whenever I make a change to this file here, Vivado will go and update itself. So I'm going to make this. I'm going to set this to 10-second delays. Actually, yeah, I'm going to set this to a 10-second delay on the clock. So the clock is going to be running on a period of 10 nanoseconds. and I'm going to unbind the stimulus from the clock by setting the stimulus to be a delay of 1 nanosecond. So every 1 nanosecond, it's going to provide the next address to the ROM, the read-in, so it's independent of the clock. All right, I'm going to run the cell, make sure that's loaded. Now I'm going to switch back over into Vivado. And I'm going to go to sources. I'm going to go to ROM loaded testbench. I'm going to go to set as top up under simulations. This is now set to top. Now, if I try to run this on my behavior and all this, on this test on all this, it's not the right test function. So don't make sure what you have synthesized and implemented it matches your test function. But for behavioral, it's going to work. So I'm going to run behavioral. That, go here, go to full view, and we can see the clock never had a chance to change because every 1 nanosecond a new stimulus was applied before the end of the test was reached. Now, this is not how you can do it this way, and there's some test things, but I want to show you what's really kind of cool. So if I switch back over into Jupyter, and I look at the cell, I'm going to change out the comments out. So now this stimulant is now rebound to the clock. All right, again, this is what we had before, or I'm going to run this. And now, I'm going to unshow that window. I'm over here. Yeah, I'm going to close that as well. I'm going to rerun the behavioral simulation. Yes. Launch. Yes. I go back over here. I go to full view. And we can see that every 10 nanoseconds the clock cycle has gone on through. And we can see now that the stimulus is now bound to the clock. So this is really a nice feature that you can now have all your documentation for what you're working on in the Jupyter Notebook. You have all the documentation, all the write-ups, all the images, the drawings, things here in the Jupyter Notebook. You can use GitHub to create a revision control system with it. You have Peeker to do all the HDL intrinsic things that you need at the behavioral level. And anytime you make changes, if everything's bound up correctly, it will be implemented those changes will automatically be reflected, which in my view 90% of the time is going to be a good thing. 10% of the time something you may not want that to happen, but this is still if used properly, this is an incredibly powerful tool. So I wanted to showcase that. Again, myHDL is one of the tools that's going to make a Python on the go-to language for all engineering. And so thank you for watching. Bye.